Okay, now today we're back in chapter 11, and we were working on that sample problem. I had you split up into small groups, and you guys were working through some of that. I've shared my iPad screen with you, so let's just take a look to refresh our memories about what was going on. We were dealing with malonic acid. Um, and I believe I was able to eventually get you guys these values for the pKs. The chat feature, I had tried to send them through to everybody, but it didn't appear to be working when you were in your small groups. The chat was only going to the people in the group that I had joined. So these are the pK values that hopefully you were working with in your group from the appendix in the back of Harris, and then the Ka1 and Ka2 values that are associated with them. And then I know as I joined some of your groups, we had the opportunity to take a look at a number line that represents the progress of the titration, where we start with our initial point. And here you note that all we've done is sort of symbolically placed Ka1, equivalence point 1 or equivalence volume 1, Ka2 and equivalence volume 2, and then the final volume for our titration on here. The only numeric value initially that we place before we give it further thought is 0 milliliters. We know that that's the starting point for a titration. So after we do that, of course, I believe we also all had the opportunity, but just out of review, we'll take a look here at the stoichiometry. Solving for equivalence volume 1. Remember that we started with the 50 milliliters of malonic acid at 0.05 molar, solved for the number of moles of acid, and then we used the mole-mole ratio from the malonic acid and the strong base sodium hydroxide for the first equivalence point to solve for that volume. We get that equivalence volume at 25 milliliters, and then just sort of you can rationalize this, or you could go through the math again, but you end up with 2 times that volume for equivalence volume 2. So that's 50 milliliters. So now we can start adding on some volumes, because we know that Ka1 will come at halfway to the first equivalence volume. And we know that Ka2 will come halfway between the 2 equivalence volumes. And we know from the list of numbers in the sequence that 60 milliliters is our final volume. So we've got some points on here, and this is the place to start, right? Because if we look back in the notes, and in a minute, I'm gonna have you guys help me remember what your groups were, and I'll give you a few minutes to regroup. And then I've gone through and done some of the calculations. We'll talk through the full problem. We'll confirm that we have the right values together. We'll draw the titration curve together and take a look at that. And then I think we're gonna jump ahead and look at an example problem from the end of the chapter that's similar, but starting with a base at high pH and going to low pH. If you look through the chapter objectives, being able to solve for these values along a titration curve at any particular volume really is one of the key learning objectives for the entire chapter 11. I would say, and not to be too disjointed in my comments, but before I continue, I posted the updated Unit 3 objectives to Moodle. They're up actually at the top of the Moodle site, and it's a PDF document that includes all of Unit 1 and Unit 2 also. And that's posted on there. So you can see the updated list of objectives for Unit 3, chapters 11 through 15. You'll note if you look in there that I have placed just a brief reference to chapter 17. That sort of, it's not yet determined whether or not we'll talk at all about 17. So that's just kind of in there as a placeholder. It won't expand beyond what I've included in there. And you'll note there's not a whole lot to it. It basically relates back to chapter 15. And the learning objective is for you to read about some examples of chapter 15 material basically in context and be able to describe it a little bit. So don't worry about that chapter 17 reference in there. We'll decide based on how quickly we progress whether or not we'll get to that. And there won't be a special homework or a lecture video on 17. It will just be doing a little bit of reading through there and having discussion about that material. So it still fits in with sort of the end of the semester. Okay, so back to this comment here. So we're in chapter 11, and I just want you to turn into your chapter 11 notes. There's the slide that we were taking a look at where I broke down in similar fashion to how Harris did. It's the slide right before we start indicators, where there's sort of a hypothetical titration curve with points A through F that are listed on there. And what we have here in this sample problem really is just a different version of that same thing, right? We've basically just squashed that down into a single axis. And we're using this number line as a means to help us understand what point we're at along a titration curve, and therefore what math we're going to use to solve for, the values, all right? So each of you were assigned into the various groups. And in fact, maybe I'll have you guys help me figure out what those were right now. I'm going to manually create, what did we have? We had 4 groups. So assign 11 participants into 4, manually create breakout rooms. Okay. Who was in group 1, the yellow group? Anybody have 0, 15, and 50 milliliters?
I think I did.
Yeah, I think that was me, Laura, and Andrew.
Yeah.
Okay, John, Laura, and Andrew. Okay, how about, what's the next group? The aqua group.
That was Brant, me, and Ethan.
That's actually group 3. So that was Corbin, Brant, and Ethan. Is that right?
Yeah.
The green group, 5, 19, and 37.
It was me, Mina, and Michaela.
So Ken, Mina, and Michaela. And that means that I must have Brenna and Fisher in group 4. Is that right?
Yep.
Okay. So what I'd like for you to do, we are going to go through, in some cases, what we'll note, for instance, volume 5 and volume 8. They both happen in the gap between the initial and KA1, and so mathematically they're going to be handled the same. I think in my solution here, I don't go through all of both of those. We just make a note that one is similar to the other and then list the pH. So what I'd like for you to do is try to regroup, look at that slide from the notes. Let's say about 10 minutes, and then regardless of where you're at in 10 minutes, we'll start working through it together, see if you got them right. It'll bring up good questions. So as you're going, I'll be dropping in on your groups for a minute or 2 at a time. But questions should be written down because it'll be a good opportunity for us to address those before we jump to the example problem at the end of the chapter, okay? All right, I'm going to send you to your groups now. All right, here I am. Any questions initially?
So
I think we had been working on one with you guys when we finished, weren't we? Or we verified some values together?
Yeah, Andrew had us check some values, and I'm pretty sure the 50 was wrong.
Okay.
But I don't remember about 15, and I think the 0 was correct at 1.5.
yeah, 0 and 15 we had correct, but 15 we had a little bit to go, so I just kind of threw out an answer just to see if I had something and it was wrong.
At 0, it seems to me, did you guys give me 2 values and one of them was right and one of them was wrong?
Oh yeah,
So
Mhm.
the correct one that I have is 2.11.
that was yeah, that's Andrew's. Yeah,
Okay.
Yep.
there we go.
And then you said 15 you thought you had correct also?
Yeah, 3.023.
Yeah, I have 3.03, so that sounds good. So you're working on 50. Do you guys know how you want to approach that, or do you have any questions?
Trying to remember what my math here is doing.
I can swing back in too. I'll give you guys a few minutes to look it over.
Okay.
Sure.
I think so.
Hello.
Yeah, but hello. Okay.
I think did we get all of them already?
Did we get the last one?
You
I
guys
feel
want
like
to
we
check
had-
your values quick and see?
Well, I feel like we had different numbers last time. Like, I don't know, maybe I just wrote it down weird. That could honestly be it. But I have like 19.3 written down.
Yeah, we have 5, 19.3, and 37.5, I think.
Yep,
Yeah.
that's what I
Oh.
have. Yep.
Okay. But I'm just all
So
right.
what's the pH that you guys got at 5?
2.25.
Okay,
Yeah.
that's good. How about at 19.3?
3.38.
Yep, that's what I have. And then your last one, 37.5.
That's just pKa2, so 5.69.
Yeah, 5.70, 5.696. Yep. Yep,
Yeah.
that sounds great. So if you understand those, great. You could start talking about other ones. You could start, if you have homework stuff you guys want to chat about for a few minutes, you have a couple minutes to just kind of reacclimate to either the problem or think about something else too.
Yeah.
Okay?
Are we gonna have to are we gonna like explain this to the class, or are you gonna do that, or like wondering if I
I
have to like-
probably will have you guys do a little bit of that, but I'm gonna also walk through it.
Okay. So just kind
So-
of like a brief sort of just like, this is kind of what we did because this, blah, blah, blah.
Yeah, sort of. Like I'll probably ask some questions about how you approached each one. And in cases like for instance, the 19.3 is similar to the 15.0. And so the group that has the 15.0 might have some input too. And so it'll be a bit of, kind of a
Okay.
discussion, if you will.
Yeah.
Okay.
Okay, sounds good.
All right.
Okay.
I'm going to jump into a different group.
Yeah. All right.
Hello.
Hi.
Any questions?
We have our 3 that we did. We kind of went over what we did
Okay.
and what we
Did
did.
you verify them with me last week, or do you want to do that now?
Sure.
I don't know if we ever verified. You just said that our process seemed correct, I think.
Okay, so let's take a look at the actual values you got.
All right. So at 8 milliliters, the pH is 2.52.
Yep, that's what I have.
And then at 25, we got 4.28.
That's what I have.
And then at 56.3, we got 11.77.
Sure. I have 11.7 without an added digit, and I don't know why I didn't carry a digit. So it's possible. I think I maybe did that in my newest solution that I'm going to show here. So it's possible I'll show that digit today. It's just not in my old notes from years ago when I first did the problem.
Gotcha.
So it sounds good. As we go through it as a whole class, I'll just be asking sort of logic at each point. And so just chime in when you guys, know why you approached it the way you did, what equation you used, how you framed that particular volume and solved it. Okay.
Gotcha. Sounds good.
All right. I'll see you guys in a few.
Yep.
You're pretty much writing definitions.
Hello.
Hello.
How are you guys doing?
Well, good.
Do we have values solved?
We do. We have values for all 3.
Do you want to check them?
Yes.
Okay.
So for 12.5, we got a pH of 2.85 because it's the same as your pKa1.
Yep.
At 27, we got a pH of 5.54.
I have a different one. My let me see if I solved for that in this example and see if we can talk through it quick. This was at 27, you said?
Yeah.
Mhm.
Okay, so tell me, what did you do at 27?
So we did the Henderson-Hasselbalch equation. So pH equals 5.696, and then we did plus log. And then I have, this might be where I messed up. I have at the top 27 times 0.1, and then on the bottom I have 77 times 0.05 as the values, but I don't think that's actually what I put in my calculator.
So here's what I would do. I would convert everything to the number of moles, because the Henderson-Hasselbalch equation will still work, and then you don't have to worry about changing concentrations throughout the titration.
So for moles, I have 0.0027 moles of HA minus over 0.00385 moles of H2A.
Yeah, and I think those values are not quite right.
Okay, that's
So what I have that I'll show the group in a little bit is I set up improper rice table just to do the accounting for this deprotonation. And so I started out with 2.5 millimoles of HA minus, because that's what we are starting out with at the beginning of the problem. That's what you get when you have the 0.05 molar times 50 milliliters.
Mhm.
Okay. And then the OH minus, we have 0.2 millimoles because it's 27 milliliters at this point, minus the 25 milliliters we've already neutralized,
Mhm.
right? So we're only 2 milliliters past the equivalence volume, which is sort of like saying we're resetting to 0 when we get to the equivalence volume. So we're at 2 milliliters times the concentration of 0.1, which gets us the 0.2 millimoles.
okay, that makes sense.
All right. Now, when you fill out the rest of this rice table, you basically end up with 0.2 millimoles of A2 minus over 2.3 millimoles of HA minus. And that's your log quotient, 0.2 over 2.3.
And you got those from the rice table.
Yeah.
You got those, yeah, from those. And then you just keep it in millimole the whole time?
Yeah, because since the units cross out, we don't have to worry about concentration.
Okay, perfect. Thank you. That makes
Yep.
sense.
So do the math and verify you get the same numeric value. And then if me just talking through it here didn't make enough sense, you'll see it on the screen when we go through it as a class.
Yes. So you ended up with 4.64.
Yep, exactly, 4.64.
Thank you.
Yep.
And then for 60, we got a pH of 10.74.
For 60, 10 points. That is different than what I got also, although this one I know I did not resolve. So now remember, this one is the amount of excess OH minus, right?
Mhm.
So it should be that you have 10 milliliters of excess OH minus times its concentration, right?
Mhm.
So 0.001 liters times 0.1 molar.
So I think,
And then adjusting for final volume, that might, is it possible that, did you not adjust for final volume?
so what we did is we did the OH concentration equals M times VOH minus VE over V total. And so what I got for my MOH though is we did 0.06 times 0.1 because we did the, we got it into molar. And you're saying do 0.001 times 0.1, and that's probably our difference.
You did, where did the 0.006 come from?
So we got 0.006 by doing 0.06 times 0.1, and let me try and remember what that is. So I think we converted 60 milliliters to liters, which is your 0.06,
Yeah.
and then times it by the 0.1 molarity.
Okay.
And so then that gives 0.006, and then we times that by 60 minus 50 over 110, which is the total.
Yeah, I wonder if it's an issue of order of operation, because really what we're doing is we're saying similar to the previous problem, once you've hit the second equivalence point, you're basically at a new zero.
That makes sense.
And so when you get to 60 milliliters, it's really like being at 10 milliliters of OH minus excess.
So we should have done 0.01 times 0.1.
Yeah, basically, because what you're doing is you're saying it's 0.1 molar times 60 milliliters minus 50 milliliters, right?
Mm-hmm. So then you would have gotten,
Did you get 9.96?
I have 11.96. And I think it's true. I've verified these a couple times, so I'm pretty sure that mine don't have an error in them.
did you say you got 9.96?
I got 11.96. It sounds like Fisher got 9.96 maybe.
What I got as well. So you did 0.001 times 60 minus 50 over 110.
I did, let's see what I did here. It should be 0.01 times 0.1.
Mm-hmm.
That tells you how many moles you have of OH minus.
Mm-hmm.
So you should end up with 0.001 moles of, so you should have 1 millimole of OH minus, right?
Mm-hmm.
In 110 milliliters. So the concentration should be 0.001 divided by 0.11. Your concentration should be equal to 9.09 times 10 to the minus 3
Mm-hmm.
OH minus, right?
Mm-hmm.
So then since H plus is equal to KW divided by that, 1 times 10 to the negative 14 divided by 9.09 times 10 to the minus 3 means that my H plus concentration is equal to 1.1 times 10 to the minus 12.
Okay.
And
So
then
what-
my pH is equal to 11.96.
Yeah, when I get that, I get 11.96 as well.
Did that
Okay.
math make sense how I did it there?
So, yeah,
You'll-
I think so.
You'll see how we do it. I'm going to walk through how we do it on 56.3 milliliters, and they're basically the same. So you'll get to see that in a few minutes.
Okay, perfect.
All right. I'm going to go check back in with group 1, and then I'm going to call everybody together.
Okay, thank you.
Yep.
The same thing I just done, but when I got X, which was equal to OH minus in moles, I just divided it by 0.05 liters to put it in molarity, and then did POH and pH.
Yeah.
But I guess I
But
don't know if that's right
remember,
either.
at that point, it's at 100 mils instead of 50.
Oh, is it?
Yeah, since we've added
Oh,
50
you're right.
to the initial 50.
Are you
Okay.
guys talking about the calculation for 50?
Yes.
Yeah.
Okay. Do you feel like you're getting it?
I think we are now. We were doing some different things, but okay.
Tell me about how you did the calculate. How did you set it up?
So we did a rice table, and we started with, we're trying to figure out whether we need to start with moles of A2 minus or like the molarity of A2 minus. But we basically just did the KB expression, solved for X, and then did pH from that. But we've gotten some different things, so I'm not sure what's right.
Yeah, so I would put in the concentration into your rice table because you're using a fixed KB.
Okay.
The cases where you don't really have to do that really are only when you're using the Henderson-Hasselbalch equation and you're just looking to get a ratio.
Gotcha.
Now, there's a lot of those instances, so they seem kind of like they're really common because, you know, if if you're not at an equivalence point or at a Ka, then you're using Henderson-Hasselbalch equation more or less. So, but in this case, I would solve for those concentrations, set up your Rice table, and then basically solve for X based on your KB1, which it sounds like is what you were trying to do.
We were doing that.
You just
with
had maybe the wrong values or different values in your Rice table, it sounds like.
Yep.
Okay.
10 to the negative.
This is one that I do go through in the outline here that we're going to take a look at in a minute. So if you guys don't figure it out by then, that's fine too.
Okay.
Okay.
So I did get a value, but it feels way off. So
What
I
is
don't
it?
know if it's correct, but 9.05.
That's what I have. Yeah.
Okay, that is it.
Yep.
It just felt very high, but
It jumps, remember. I mean, this is a steep
yeah.
inflection point. So
Okay.
we'll see on the, when we draw the titration curve, it's pretty remarkable that we don't actually see much of the first equivalence volume. And there's almost no inflection point we can discern based on our hand drawing, but the second one is very noticeable. So,
Okay.
okay. All right. I'm going to call everybody back to the group.
Right.
Oh yeah, I just got 9.05.
Dr. Winters, you're muted.
I don't know why it just did that. Thank you. Okay, so let's take a look. It seemed like most of you were getting all the calculations right. There were a couple of small errors here and there, but overall I thought it was looking really promising. So nice job. Even the errors that I think that we did face were pretty they're common mistakes and good opportunities to ask and answer some questions that'll help us move forward. So let me advance this up to the point where we were. I just have to let it write. I guess I can speed it up a little bit, I think. Okay. We had seen all this. We'd done the equivalence volume. Okay, so I think we were about ready to start solving. And I think let's take a moment here and walk through starting with 0 milliliters. So I'll show the calculation for either the specific volume or one that is more or less analogous to it. So for 0 milliliters, how do we set this one up for group 1? Describe for us sort of how you approached the problem and a general setup, and then we'll take a look at on the screen how it goes and address any questions that come up.
I guess I can hop in on this one. So when you are at 0 of your starting reagent, whatever you're trying to add in, we treated it as a monoprotic acid at this point. So we set up a simple Rice table. So this would just be like your your malonic acid in its fully protonated form, disassociating into one of its protons and its conjugate base. So you set up your Rice table and then use the concentration. We converted to moles, but I guess you should only be using moles when you're setting up ratios. And when you're using the Henderson-Hasselbalch equation is when you're going to be using moles as opposed to concentrations.
You can go back and forth, John, just to pause you for a second. You can go back and forth. We just need to be careful. to adjust for concentration when we need it and for dilution as needed. So you can end up with positive outcomes using it either way, but just make sure as you're working through these rice tables, you're confirming values. In particular, you know, you're fiddling with it in problems maybe from the end of the chapter, some simple ones to just verify that the answer you get using both ways is equivalent. But it is a note that I made for group 1 that Henderson-Hasselbalch equation, when we're looking for ratios, more often it's acceptable and useful to just stay in moles or millimoles. At the other points along the titration curve, I would say it's often a better idea to stick with concentrations. So, all right, continue on, John. Sorry to cut you off.
Yeah, so then from here, you set up your quadratic formula based on the products over reactants and your Ka equations. And then you solve for X. That gives you your concentration of your acid, and then it's your pH equation, so negative log of concentration of your acid, and then you can solve for pH. So pretty straightforward, this one was.
Yeah. Any questions about this? Just always got to remember, treat it as though it's monoprotic. We saw a really great example last week, I think, when I went unwittingly, I didn't realize until the end, I think it was Corbin that drew my attention to the fact that I had solved a problem through for the concentration of the fully deprotonated form, and we concluded that its concentration was indeed equal to its Ka, just like the notes suggested, and we showed that mathematically. So monoprotic is the way to go here. How about at volumes 5 and 8, groups 2 and 3? What did we do?
I can explain it. So what we did is we calculated the moles of our HA based, so we took 50 milliliters and 0.05 molar malonic acid, and we figured out how many moles we have of that. And then we also figured out how many moles of NaOH we have. And then, so we essentially did a rice table without setting up a rice table. And then we took the moles of our acid minus the moles of our NaOH to get the leftover moles of acid that hadn't react with NaOH. And then we plugged both into the Henderson-Hasselbalch with the NaOH as the B and then the HA being the leftover moles of our acid. And then the pKa being our pKa1.
Okay. So you can see here in my solution, I just made a note that we're going to use the Henderson-Hasselbalch equation and that we're going to remove some of our H2A. What Corbin was describing is setting up a rice table. I've described this for you guys also, where it's not technically a rice table because we're not really doing an equilibrium. This is actually a single-sided arrow since we have a strong base, but we're going to use it for accounting purposes anyway. In the table then, I've listed here millimoles. And the reason that we can get by with using numbers of moles rather than concentrations here is that we're not solving a quadratic equation that requires the numeric value to have the right units for the answer, right? So if we were to try and do this in one of the cases where we have a quadratic or where we're even able to simplify one of those have to be solving for it in the units that we want the answer to be in. So we can't just substitute in moles for concentration units. But here we can. It's just an accounting mechanism, a spreadsheet, if you will. And note that I show the calculation here for the number of millimoles of H2A that we start with. I don't show the calculation for the 0.5 millimoles of hydroxide, but that's simply what we're given in the problem. That's our 5 milliliters of hydroxide times its concentration to solve for the 0.5 millimoles of it. We go through the accounting knowing that we lose all of the H2A that the hydroxide can react with. So our hydroxide concentration goes to 0 and our HA minus goes to 0.5. then it's just, as Corbin said, the Henderson-Hasselbalch equation. It sets up the same way for our next volume at 8.00. Now, something I want to make a note of for you here is that this assumes that there's no pre-equilibrium established with Ka1. So you might be asking yourself, yeah, but you're saying we're starting out with 2.5 millimoles of H2A, and then we're reacting, consuming 0.5 millimoles of that because of the added base. But in the last step that John just described, we know we already consumed some of it. We consumed a value equivalent to 1.42 times 10 to the minus 3 molar. And so that wasn't available. It was already consumed and neutralized. That's true. These values assume that that is not happening to an appreciable, significant extent. And so I would say that at this Ka1 value, what is it numerically, 2.847, we're talking about concentrations, you're talking about 10 to the minus 3. This is probably kind of a threshold where if your Ka is any lower than this, you definitely would have to account for it. And in fact, you can see here, the value that I put below the circled answer is 2.59. That's if you go through this calculation and assume that we do establish a pre-equilibrium with Ka1, account for that, and then react the hydroxide afterward, okay? So for weaker acids than this, they would not dissociate enough naturally on their own to need to account for that, but for stronger acids, they definitely would. Everybody follow that logic? I think I do the same type of calculation in the next step potentially, but it's worth noting that for 8 milliliters, we have similar math. What's the pH for 8 milliliters for group 3?
2.52.
2.52, that's what I have also. Okay. Let's see
what would be the Ka in which you, like, what is the stopping point for not, for assuming no pre-equilibrium?
Well, I would say there's not a hard and fast rule to this. I'm saying that in terms of our practical application of this, I want you to assume that you don't have to worry about the pre-equilibrium. On here, I wanted to address it because I thought some of you might be wondering, well, why didn't we talk about what the calculation we just performed, and why didn't that play into this? It seems like it's sort of a little bit of smoke and mirrors, and it's worth saying that in this particular problem, it is a little bit of that. We're sort of holding to a double standard, and it's actually pretty significant. So we're going to just kind of turn a blind eye to it for this problem and problems going forward. There's a chance that Harris will want you to account for that in a problem, whether it be a practice problem. I haven't looked over the homework. So if you're just not getting the value that he is, especially for that first, up to the first equivalence volume, you're just off by a little bit. This is something worth considering, that maybe there was a pre-equilibrium that you need to account for. Okay. Let's see what the next volume is that I solve here. I don't think it's 8. Oh, I guess I do go through 8, maybe. So let's take a look at 8. It's the same kind of math, same kind of table we're setting up. In green in the lower corner there, that's actually with the pre-equilibrium accounted for. So notice how much that changes it. It goes up to a pH of 2.8 instead of 2.52. After this particular calculation, we're not going to worry about accounting for that going forward, but I thought it was kind of interesting to note that up to this point.
Wait, so I have a question. So
Yeah.
the way to account for that pre-Ka equilibrium would just be to set up like a rice table with how much of the acid would dissociate initially?
Yeah, yeah. And I can't remember, can you guys see my cursor when I have it on there or no?
Yeah.
Yeah. So do you see this value here, the 2.5?
Mm-hmm.
This value assumes that all of the initial 50 milliliters of malonic acid is still in the form H2A, but it's solubilized, so it's aqueous, right? In the previous step, we showed that a portion of that, 1.4 times 10 to the minus 3 molar, actually is consumed or neutralized and forms this HA minus. So to account for that pre-equilibrium, we subtract this number of millimoles, once we've converted it to millimoles from concentration, from this 2.5. It ends up being something like 2.3, somewhere in that range. And then we continue the calculation as we did it in this example. So then from that 2.3, we're subtracting another 0.5, which further reduces these values. So, and then we do the same thing over here. In fact, we could see what it is. What is 1 point? What's 1.314 plus 0.8? It should be 2.114. So that 2.114 is actually the value that goes here.
Okay, that makes sense then.
Okay. I would argue that if the amount of difference based on the pre-equilibrium is in the couple of hundredths of a pH unit, I wouldn't worry about it. Okay. The error in your pH probe is likely as big as that over time, just between measurements and things. So I wouldn't worry about it. It means that probably our Ka is about an order of magnitude away from that being possible. So anything in the 10 to the minus 4, no need to worry about it. 10 to the minus 3, it has a significant but not overwhelming contribution. Anything in the 10 to the minus 2 and bigger than that, and you're talking about, like, you absolutely have to worry about it. That would just be my thought based on what we've observed here anyway. Okay. All right, let's take a look then. So you'll note up at the top, I've listed the pHs. We'll do a reaccounting of those at the end because I'm going to clear the slide to continue the math. And then we'll draw the curve. So we'll continue making a note of that. We've done now 0, 5, and 8. What about 12.5 for group 4? Tell us about it.
Fisher, do you want me to take this one or do you want to do 12.5?
You can take it.
Okay, cool. So for 12.5, what we did, so your pH equals your pKa1 at this point because it's half of your VE1. And so 12.5 is really simple because it just equals your 2.847, which is your pKa1.
Okay. So that's the benefit of having drawn the number line, right? I didn't even show any math on mine. I think, Brenna, thank you for describing here Henderson-Hasselbalch equation. We know based on that pH, the equation simplifies to pH equals pKa1, right?
Yeah.
Okay. All right. Then let's take a look at, I think we're going to do 15 next. And 15 and 19.3 should be similar math. So group 1 or 2. Tell me about what you did.
So for 15, we did, knowing that it's not yet to the first equivalence volume, we treated it as a mixture of H2A and then HA minus, and then used the Henderson-Hasselbalch equation.
Okay. So really you end up with the same math as we saw for 5 and 8. So I brought the screen back up for these so that we can take a look back at them. It's a matter of now, rather than having our base be the smaller value on top and our acid be the larger value on the bottom, those flip-flop. We end up starting in that log quotient, we end up having more base than we do acid after the pKa, but before the equivalence volume. And so we end up getting negative values coming out of the log, right? Okay, so that math looks basically the same. We know that we can only go up to where we have this 2.5 millimoles. And stoichiometrically, that comes at what point?
Do you have this written down?
Do I have what written down?
This example?
No, I just came back to 5. What I had here I see is I jumped up to 25. It's the same as 5 and 8.
What are you like subtracting then? I guess I'm confused because I get that, like, I'm kind of confused. It's hard to
Okay.
follow verbal.
So set up here. Replace 5 here with 15.
Yeah.
Then here we end up with the same reaction. We end up with 2.5 millimoles again. Instead of 0.5 millimoles of hydroxide, we have 15 times 0.1, so 1.5 millimoles. And then the rest of the problem sets up the same, just with new numeric values. So we should end up with 1 millimole of H2A. We should end up with 1.5 millimoles of HA minus. Our pH should equal then 2.847 plus the log of 1.5 divided by 1. I get 3.02.
Makes sense.
Okay. We would set it up the exact same way for 19.3, just with different numeric values in the Rice table. Does that help?
Yeah. I just thought I heard you say that you have more NaOH than you do your original acid, and I got really confused.
No, I maybe misspoke, or you have more of the HA minus, that base, not the strong titrant base, but the conjugate base.
So it's your actual HA minus, not your base being put in for your
Yeah,
base.
so
in your
I
hexagon.
probably just said base sort of generically, but needed to be more specific.
Then what is that pH?
I got 3.02.
Okay.
Is that what our group got for this one too? I think it was, right?
Yep.
Yep. And then for pH 19.3, what did you have on that one, group 2?
The volume of 19.3?
The pH at the volume of 19.3.
Oh, 3.38.
Yeah, okay. 3.38. Again, we'll do an accounting. We'll list these out later. We'll go through them. All right, let's take a look then at 25. What do we do at 25? Group, what is that? Group 3?
Yeah, so what we did is we just took the first equivalence point equation, and it's the big one that's like the square root of K1, K2, F plus K1, KW divided by K1 plus F.
Absolutely.
Hydrogen concentration.
So we know at that point, I'll just add to that, we know that at that point, all of the H2A is converted to HA minus. The equation that, was that Fisher that was talking there? Oh, no, that was Ethan.
No, that was me.
Sorry, I was trying to figure out from voice. I had not been watching close enough on the screen. So what Ethan was describing is that was the equation I have written here, H plus ion concentration. Remember that this equation is good at equivalence points. So we use it in 2 different forms or 3 different forms, depending on di or triprotic. We talked previously about how to determine the K values to use. So we have K1 and 2 formula concentration. We solve for it and we end up with a pH of 4.28. Okay. Group 4, describe something for us about 27 milliliters. How did we set this up?
So for 27 mils, it's basically the same thing as what Corbin just described, or what you guys just described for 15 and for 5 and 8. The thing that we messed up on, however, is that because you've passed an equivalence point at 25, you have to kind of pretend like you now only have 2 milliliters instead of actually having 27 milliliters. So you do a little rice table and you'll get that there's 2.25 millimoles of HA minus and 0.2 millimoles of OH minus. Yeah, and then so you would do the Henderson-Hasselbalch of pH equals 5.696 plus log of 0.2 over 2.3, and those are in millimoles, and you can keep them in millimoles because they cancel out anyway. So we didn't count moles.
Here, I was just trying to share my screen and it like conked out on me. So let me try again.
Okay.
I'll walk back through this. So I thought that was a really good opportunity to take a look at this because I think it's a reasonable thing to be a little confused about and maybe make a misstep. And that was what Brenna was just describing about sort of realizing that at each equivalence point, you're kind of resetting to 0. The reason for that, I'll just describe here maybe in a slightly different way, and that's because we have a new reaction that we're considering. The new reaction is not H2A going to HA minus. We're now considering HA minus going to A2 minus, right? And so that reaction switches over at the equivalence volume, which means that now we've only got 2 milliliters of this new titration. It's almost as though up to equivalence volume 1, you were doing a single titration, then you automatically switched and you're starting another titration. And so you're accounting for only the amount that you've titrated since the last equivalence volume. So I set up another rice table to do some accounting work here. We're all becoming great accountants, I know. Note here that we start out with the 2.5 millimoles of HA minus because that's what we started with at the very beginning of H2A. We've converted 100% of it to HA minus at the beginning of the second titration, that second reaction after the equivalence volume. This 0.2 millimoles, this is coming from the math here that I show, 27 milliliters minus the 25 to get to the first equivalence volume is equal to 2 excess milliliters times its concentration, gives me 0.2 millimoles. Okay. Then we do, just as Brenna was describing, exactly what we did before, where we're going to use the Henderson-Hasselbalch equation. Since we're now in a new region, we have to adjust and use a different pKa, but otherwise everything sets up the same. It starts to look fairly familiar in a hurry. We end up with a lot of volumes along a titration curve that are done in this exact fashion. Any volume that's not an equivalence volume, not at a pK value, and not 0 milliliters is done with the Henderson-Hasselbalch equation. Okay. Any questions about that? All right, how about 37.5, group 2?
So for 37.5, it's just equal to the pKa2, which is like 5.696 or 5.7 for pH.
Perfect. Easy math. That one's one you can do in your head, right? There's something so satisfying about getting to those. You work so hard at the other volumes, and then you get one, you get to just like write down the pH, and it's so wonderful. Okay. How about 50 milliliters?
So for 50 milliliters, since it's the second equivalence point, that means that we can essentially assume that all that is left is A2 minus, and based off, and then based off of that, we are able to do the same thing that we did with the first one, so it's 0, and treat it as if it's a monoprotic system. And using just a rice table, we can go in and solve for this change in X, which gives us the concentration of HA and OH minus. And since we're solving for OH minus, we end up solving for a POH, which we can convert to a pH, which gives us 9.05.
Perfect.
Sorry, I also forgot that for this one, you have to use KB instead of KA.
Yeah, I think you referenced KB, maybe not as explicitly as you wished you had, but I followed that. I think it was a good description. You'll see here that we use KB1 because this is Ka2. So I've written out that reaction here, and then I stopped as I got the initial conditions written in. Below the rice table note, this is where I just do a dilution equation. M1 times V1 over V2 equals M2. So our concentration of A2 minus, because we are at twice the total volume as when we started, is half of the concentration it was at the beginning. So notice we're at 0.025 molar. Our initial concentration was 0.05. So this is exactly what we expect. Initial concentration of HA minus is 0. Initial concentration of OH minus is 0. Okay. Set up the rice table the rest of the way. Of course, we didn't previously solve for our KB values, so we have to do that. Andrew was describing that this gives us actually OH minus concentration, and so we have to solve either from POH or from OH minus for our pH. Last week I went from POH. Today, just to switch it up, I went from OH minus concentration in my calculation. You can do either. I end up with a pH of 9.05. Okay. 2 volumes left. Let's take a look at those quick, and then it looks like we're out of time for today. Okay, so tell us our groups 3 and 4. Tell us about 56.3 and 60 milliliters.
Basically, the pH is determined by the excess hydroxide concentration. And so it's just whatever the concentration of hydroxide that you have, that's going to be, or excess hydroxide is going to be your pH.
Okay, so excess hydroxide, as I've noted here, at 56.3, I'm going to show the calculation, though it's worth noting it's identical at 60, just with numbers that we start with are a little different. So the start of this here, we start out with the 6.3 milliliters. Why 6.3?
Because you have to subtract it from your 50 mils of acid that it takes to get to the equivalent point.
Yeah, so we only have 6.3 excess because the first 50 milliliters were all consumed in neutralizing our acid, right? So I have 6.3 milliliters of excess times the concentration. We end up with a number of moles. Then I'm going to set up a simple accounting table here again. Notice that all of my hydroxide then dissociates to form, all of my sodium hydroxide dissociates to form hydroxide. So that means that I can, in this line here, about the middle of the screen, notice that all I've done is taken my 6.3 times 10 to the minus 4 moles of hydroxide divided by the total volume, which is 50 milliliters of starting acid plus the volume that I've added of titrant. In this case, it's 56.3. So the concentration is equal to 6.3 times 10 to the minus 4 moles over 0.1063 liters. We're able to get that here in 5.93 times 10 to the minus 3 molar hydroxide. And then in similar fashion to the last step, we convert concentration of hydroxide to concentration of H plus and solve for pH. If we were to do this at 60 milliliters, we would simply replace this with a 0.01 liter at the top and allow that then to work its way down through the math here. Other notable change is, of course, that this here has to become 60 milliliters so that the total volume, instead of 0.1063, becomes 0.110. But those are the only changes. What was the pH group for from 60 milliliters?
We got a pH of 11.95.
There you go.
Just a little bit different.
So let's write these up. I'm just going to make it right below each of the volumes on the slide here. I'm just rewriting in the pHs that we solved for. And then on one of the slides here, I gave you a 2-axis coordinate system to plot a titration curve. So to finish up here today, what we're going to do is just try to use that label the abscissa as volume titrant added in milliliters and place some of the values on there. And then label the ordinate with 15 marks over the pH scale and with an axis title of pH. Just eyeball the volumes the best you can, just like I've done here. Once you've done that, you can start placing the pHs on there. Do the best job you can to pinpoint their location. Once they're all on there, you can draw a line. I like to draw on a hypothetical line. It's worth noting, I think, that at least in such a crude drawing, we don't necessarily see an inflection point for the first equivalence volume. It's likely that if we did this really well in the lab, we would at least see some sign of that equivalence volume, but at times you don't see any. Okay. Now, what we're going to do next class period as we wrap up here, you can finish making this plot or you can look back at the video of this. I'll post the whole class video so Jesse can watch back the lecture. We're going to talk a little bit about the different regions of this plot next class period. I would like to quickly go through and give you a chance to try to do some similar calculations in a diprotic base system just to try to burn this into our memory. That's going to be problem 11-23, I think. And then my thought was maybe taking some time in small groups for you guys to work on your homework 6, which is a spreadsheet of a diprotic acid-base titration curve. Would that be functional to have breakout groups and have you work on your spreadsheets and do that? I mean, I'd want everybody to be making their own spreadsheets, but I also want to have you guys benefit from being able to talk about it together. So we can either do that or we can move on, but we have plenty of time in chapter 11 to pause and let you guys work on some things, come up with some questions and get yourself into a little trouble. And then I can help you get out of the trouble before we move into chapter 12.
Sounds like a good plan.
Then I think on the syllabus, it seems to me the revised schedule, we're still in chapter 11 on Monday. Is that right?
Yes. And then chapter 11 homework is due on the 22nd, which is Wednesday.
That sounds about right. So my plan is that we'll do all of our discussion of endpoint detection and indicators on Monday. And be ready to jump into chapter 12 next Wednesday. Okay. All right. Thank you, guys. Any last questions before we?
Sorry, yeah, I did have one last question. I hate to be that guy, but
no, you're fine.
We didn't do, so you know how at 0 milliliters we did the rice table to figure out the difference when it was, how much of it was dissociated. The reason we didn't do that at the end here with the NaOH is because it's a strong acid, whereas if it's a weak acid, we would need to, or a weak, sorry, base.
Yeah.
So if it was a weak base, we would just need to do that again after the final equivalence point.
Yeah, although we don't do, with two competing equilibria, we're not going to do a problem where it's a weak acid and a weak base together.
Okay.
One of them will basically always be strong so that you can predict that once you've reached the equilibrium, you will have excess, either H+ or OH-.
Sounds good.
Okay. But yes, that's exactly why. Good point to make.
Okay.
Any other questions? All right. I will see you guys on today's Wednesday, I guess. So I'll see you on Friday.
Bye.
Bye.